3.11, prove that the following sequences are monotonic, they determine whether they are bounded, and find the limit in case they are. So 3 things, okay? Monotonic, bounded, limit. Okay, 3 things we have to do. And then we have 5 sequences, okay? So the first one, as you can see, it's the square root of 2, and then this the square root of 2 times the square root of 2. Okay, so square root of 2 times the previous element, and then the square root of 2 times the previous element. So we can write this like, this is a sub n plus 1 is square root of 2 a sub n, okay, the previous element, and with a sub 0 being 1 of, or square root of 2, okay, and go on. Okay, so, well, how to do this kind of exercises? Okay, this is a an exercise that we will do over and over again. It's very typical that this kind of problems appear in the exam. Okay, so you have to learn how to do them properly. Okay, so first, what we do with this is first we think, assume. Okay, assume a sub n has a limit. Okay, and we'll call this one a. Okay, so and then we take limits in this recurrence expression. Okay, so this is a, and this is square root of 2a. Okay, so now in order to solve this we squared both sides, and we have 2a, or a squared minus 2a is 0. Take a common factor of a, and then we have a minus 2 equals 0. So 2 possible solutions. Okay, a equals 0 or a equals 2. But then which of the 2 is the limit, if there was a limit? Okay, so if a sub n had a limit, okay, then it could only take these 2 possible values, 0 and 2. Okay, but we don't know if the sequence has a limit yet. Okay, and we will see some of these examples that don't have a limit. Okay, now how do we prove that this sequence has a limit? Okay, so the problem is giving us the hint. If we have seen in theory that sequences that are monotonically increasing or decreasing and then they are bounded, we know for sure that they have a limit. Okay, so we are going to prove that this sequence is bounded. Okay, so let's leave this like this. Okay, so it's a is equal to 0 or 2. Okay, a sub 0 is square root of 2. So what I'm going to prove is that a sub n, the sequence is bounded by 0 and 2. So it's a sub n is greater than 0 and a sub n is smaller than 2 for all n. Okay, how do we do this? Well, our old friend induction principle. Okay, so we test it for the n equals 0, it's the smallest one. A sub 0 is greater than 0, that's correct, and a sub 0 is smaller than 2, that's correct. Now we assume it is true for some n, so we assume a sub n is greater than 0 and a sub n is smaller than 2. Now what happens with n plus 1? Well, a sub n plus 1 is square root of a sub n, 2 times a sub n. Now we have assumed, this is the induction hypothesis, that this is greater than 0, so 2 times a sub n is greater than 0, but the square root of something that's greater than 0 is going to be greater than 0. So this proves the first result. And for this one, 2 times a sub n, we have assumed that this thing is smaller than 2. Okay, a sub n is smaller than 2, but 2 times 2 is 2 squared, or 4. Square root of 4 is 2. Okay, so this proves the result. Okay, a sub n is greater than 0 for all n and is smaller than 2 for all n. Okay, so this sequence is bounded. Okay, so if we start here, let's say we have all these terms 0, 1, 2, 3, and then on and on, and we have this is 2 and then this is 0, then this first term is something around here, okay, a sub 0, and then 2 times the square root of 2, this thing seems to be a bit greater and greater. So if you compute this using a calculator, you see that every term is increasing, okay? But we have to prove this rigorously, okay? And then this is a very typical thing that happens in exams, that nobody proves this, okay? But you have to prove that the sequence is either going to 0 or to 2, okay? It's either increasing or decreasing, okay? How do you prove this? Okay, you have to compute the subtraction a sub n plus 1 minus a sub n and see if this is smaller than 0 or greater than 0. If it's greater than 0, the sequence is increasing. If it's smaller than 0, then the sequence is decreasing, okay? Well, now this is the square root of 2an minus an. We know how to deal with this. You multiply by and divide by the square root of 2an plus an, and then in the numerator you have the difference of the squares, okay? And then we have common factor of take common factor of a sub n, so we have a sub n 2 minus a over square root of a 2an mass plus an, okay? Now, and again, a tip forever in this kind of exercises, the numerator that you will end up with always is the same as the equation that you obtained when you were computing the limits. So if you remember when we were getting the limit here, assuming the limits, taking the limits in both sides, we had 2 times a, so it is a squared 2a, and then we have a 2 minus a equals to 0, okay? So the same expression, okay? Remember that. So this is a useful thing. So now, is this greater than 0 or smaller than 0? Okay, a sub n is actually greater than 0, we know. We have proven it. 2 minus a sub n is, sorry, this is 2 minus a sub n. A sub n is smaller than 2 actually, so this is going to be, greater than 0 again. Okay, greater than 0. And these two things, they're positive, so positive. So everything is positive, the product is positive. Okay, so then we have a sequence that is monotonically increasing, okay, for all n. The a sub n plus 1 is greater than a sub n, so it's increasing. It's between 0 and 2, so it's bounded by 2 above, so it's increasing, it starts below 2, so the only limit it can take, and it will take it, is a equals 2. Okay? So this strategy, the same that we have used here, is the same that we will need for the rest of the problem. So let's go with it. Now a sub n is square root of 2 and then square root of 2 plus the square root of 2. So it's square root of 2 plus the previous term, right? So it's square root of 2 plus a sub n. Sorry, and this is a sub n plus 1. Okay, so just like before, assume that this has a limit. So we take limits in both sides. So we have a is the square root of 2 plus a. Now we square both sides. A squared is 2 plus a. And then this is a squared minus a minus 2 equals 0. And then if you kind of try to solve this, you will get a factor to possible limits, a minus 2 and a plus 1. Okay, so either a is 2 or a is minus 1. Okay, but we don't know. So now we have to prove that the sequence is bounded. Okay, so let's see if we can prove it's bounded between minus 1 and 2, or maybe between 0 and 2. Why not? So because the first term, a sub 0, is the square root of 2, and it seems that, you know, every time you're summing things, so it doesn't look that it's going to be negative at any point. So a sub n is greater than 0. Again, using induction, a sub 0 is greater than 0. Okay, yes, it's true, and assume it's true for some n. Is it true for n plus 1? Okay, so a sub n plus 1 is the square root of 2 plus a sub n. Now we have assumed that a sub n is greater than 0, so this is greater than the square root of 2, or in other words, it's greater than 0. Okay, so this proves the result. A sub n is greater than 0 for all n. And now let's see if a sub n is smaller than 2 for all n. So yeah, a sub 0 is smaller than 2, the square root of 2 is smaller than 2. And then assume this is true for some n. Is it true for a sub n plus 1? Well, again, we have this expression for a sub n plus 1. We have assumed a sub n is smaller than 2, so this is smaller than 2 plus 2. 2 plus 2 is 4, the square root of 4 is 2, so this is smaller than 2. Okay, so again, this completes the induction step. So we have proven that a sub n is between 0 and 2. Okay? And now, the last step is we need to prove that the sequence is increasing or decreasing. Okay? But yeah, it seems like it's increasing. Okay, you are summing something. Okay, so let's prove this. We can't say, well, you know, you sum things and it seems like this is greater than this, so the sequence is increasing. You have to prove this. Okay, so you have to do this step, please. A sub n plus 1 minus a sub n. A sub n plus 1 is 2 plus a sub n minus a sub n. And just like before, we multiply and divide by the converse, so this is 2 plus n minus a sub n squared, and then 2 plus a sub n plus a sub n squared. And as you can see, this is the same as the previous polynomial, but with the sign. In this case, the sign is different, but doesn't change. So this, and we have done this thing here, so this is a minus 2 times a, sorry, this is 2 minus a. 2 minus a times a plus 1 divided by 2 plus a n plus a n squared. Okay? So the reason that I changed the order here is to make the signs be correct. Okay. Now 2 minus a, we know that a, sorry, this is a sub n and a sub n again, sorry. 2 minus a sub n, we know that a sub n is smaller than 2, so this is going to be positive. A sub n plus 1, a sub n is positive, so if you sum something to something positive, it stays positive. And the denominator is positive because every term is positive. So everything is positive. So a sub n plus 1 minus a sub n is positive. It means that the sequence is monotonically increasing. It started at square root of 2 and it's bounded above by 2, which is one of the values that it could take as a limit. So if a sequence starts below 2, increases, and is bounded above by 2, it means that the sequence has a limit and it is 2. Okay, it's the only possible result. Now, for 3, u sub n plus 1 is 3 plus u sub n over 2, and then u sub 0 is 0. Now again, assume this has a limit, so we take limits. U, call the limit u, so let's call it limit when n goes to infinity of u sub n is u. U is equal to 3 plus u halves, so this is the same as u halves equal to 3, the same as u equals to 6. Okay, so in order to prove that the sequence actually converges to this limit, we need to prove that it is bounded above by 6, for instance, and then that is increasing from 0 to 6. Okay, so let's prove this thing. First, bounded. So let's say it's bounded by minus 6. Sorry, u sub n is smaller than 6 for all n. Now we have to use induction. Assuming it's true for, well, first check it's true for n equals 0. U sub 0 is smaller than 6, that's true. Now assume it's true for some n. Is it true for n plus 1? Okay, so u sub n plus 1 is 3 plus u sub n over 2, and we know, we have said that u sub n is smaller than 6, so this is 3 plus 6 over 2, which is 3. 3 plus 3 is 6, so this is 6. So u sub n plus 1 is smaller than 6, so this is correct. Okay. So we have said that, proven that the sequence is bounded above by 6. Now the last step is to prove that the sequence is actually increasing. So as before, u sub n plus 1 minus u sub n is 3 plus u sub n over 2 minus u sub n. Or in other words, 3 minus u sub n over 2. And if we take everything in the same fraction, 6 minus u sub n. But we know that u sub n is smaller than 6 for all n, so this is going to be positive. So u sub n plus 1 minus u sub n is positive, then the sequence is increasing monotonically. Okay? So it starts at 0, it increases monotonically, it's bounded by 6 above, so it has a limit, and the only value of the limit it can take is this one. Okay? Now for the fourth one. Fourth one is similar to this. U sub n plus 1 is 3 plus 2 u sub n. U sub 0 is 0. Okay, we do the same thing. Assume it has a limit. We compute the limit, taking limits in both sides. So then we have minus u is equal to 3, or in other words, u is equal to minus 3. Okay? So now you could say, well, you know, this limit is going to be minus 3. So in order to do that, starting from 0, you would have to go to negative numbers, okay? But if you look at this, this is 3 plus 2 times u sub n. So then you have the sequence u sub n from n equals 1 to infinity is 0, and then the second term is 3, and then the second term is 2 times 3, 6 plus 3 is 9, and then 2 times 9, 18 plus 3, 21, and it seems to be increasing. So there are no negative numbers. So can we say that this sequence is increasing forever? Okay. Well, it doesn't seem as if this sequence is bounded above. And so first of all, let me try and say this sequence is increasing. Okay, let's prove it. So u sub n plus 1 minus u sub n, this is 3 plus 2 u sub n minus u sub n. And so then we have 3 plus u sub n. But, well, we can prove that u sub n is greater than 0. Okay? It's easy to prove, again, using induction. Well, let's prove that u sub n is greater than minus 3. Okay? U sub 0 is greater than minus 3. That's true. Is it? We assume it is true for n. Is it true for n plus 1? Well, u sub n plus 1 is 3 plus 2 u sub n, which is greater than 3 plus 2 minus 3, so it's minus 6, greater than minus 3. Okay. So we have proven the result. This is greater than minus 3, so 3 plus u sub n is going to be greater than 0. Okay, I hope it wasn't very confusing. So the sequence is increasing. Okay, u sub n plus 1 minus u sub n is increasing. So suppose u sub n had an upper bound. Let's call it n. Okay. Now u sub n is increasing and it has an upper bound. Then our theorem says that u sub n would have to have a limit. Okay, so it's a bounded from above sequence and it's increasing. It should have a limit, but the only limit it can have is minus 3, which is not possible, but because the sequence is greater than minus 3 all the time and it's increasing, so it can't be. Okay, so it can't be. U sub n can't be bounded above. Okay, because the only possible limit it can take is minus 3. Okay, so u sub n is not bounded, so it grows to infinity. Okay, the only bound it has is plus infinity. Okay, and